All right, so yeah, the question earlier was, will every lab be RStudio? And the answer to that is yes. If we use RStudio on exam questions, can we just quote from our XXX? Okay, so the answer is different for quizzes and exams. The midterm and final exam, which are worth a lot, is multiple choice. So there's no option to write any explanation. You either picked the correct multiple choice answer or you did not. For the quizzes, you'll be graded, and you might get partial credit for your work if your work is correct or something. And so, you know, if you do it from RStudio, that's fine if you get the correct answer. But if you get the wrong answer and you don't show any work, then you won't get any partial points, and I think that's also just how it goes there. How much work would we need to show on the exams quiz if we use R or a calculator? So again, yeah, exams are multiple choice, and the quizzes are short answer. You know, a lot of them, and I should note that, you know, a lot of these short answer questions are a lot of them are you got it right or you got it wrong. So you don't have to show a ton, but it can be helpful. Okay, first lecture, I have not given the first view answer yet. I'll do that shortly. Someone says that they are completely unfamiliar with R. Can we go over the basics in office hours? Absolutely, come to office hours. So, you know, I'm not expecting anybody to know anything about R prior to enrolling in this class, okay? I'm fully aware that we are teaching you a brand new program, a brand new technology and programming language. And so, so this very first lab is intended to be simple, but in the same way that, you know, if you guys drive cars, you know, your very first behind the wheel lesson was probably driving around in a parking lot. But even then it can feel overwhelming, right? Just because there's a whole lot of things that you have to be aware of, right? There's you know, in a car, there's, you know, the gas and the brake and the turn signals and the lights and the steering wheel and all of these different controls and all of that. And even something as simple as just driving around a parking lot can feel overwhelming. And the same thing is true for anything new that you pick up. And in this case, it's going to be R and RStudio. And, you know, this first lab is intended to be very simple, but again, because it's brand new, it can feel overwhelming. And so my first slide is we are here to help, okay? You know, I want to acknowledge that the labs can feel overwhelming in the beginning, and that's totally normal. I mean, some of you guys are doing fine, right? Some of you guys are like, oh, I don't think it's hard at all. Okay, well, you know, I'm happy for you if that's the case, but others of you might feel like you're completely lost. You know, what is all of this stuff that we've got to type, you know, typing into the console, you know, that feels like something only hackers do in movies or something. And it can feel overwhelming. And again, so the TAs and I, we are here to help. Come to office hours and we're happy to help. There's also a campus-wide discussion forum. Okay, I've linked to that on CCLE under week 1. You can click this campus-wide discussion forum, and this is what we have. About maybe a fifth of you have registered, and no one has asked a question yet. And I'm going to direct you, if you send me an email with a question on how to do R or how to do some kind of homework assignment, I'm not trying to be rude, but I might just say, please post your question on CampusWire, okay? And that way, you know, whatever question you have, probably other students have the same question, and that way, you know, when someone answers it, whether it's me or the TAs or another student, that answer can benefit that answer can benefit other students as well. So so ask your questions on CampusWire. I think this is superior to like a group chat. You know, I don't know if somebody has created a group chat, but as you know, as far as group chat goes, there's no organization. It's just kind of this huge streaming mess. And so the CampusWire forum is a way for you to kind of post questions and organize things, and it's supposed to be a place where you can help each other out. So so that's what we've got going on there. Okay, so don't hesitate with your questions. Okay, the code 8123 doesn't work. Is that right? Okay, let me see what's going on. It works for you? Okay, so this is stats 10, settings, invite by link 8123. That's what it says. Okay, try signing in. Okay, you get a code in the email and then I'll ask for 8123. Yeah, oh yes, you do have to use your school email. That's yeah, that's a huge limitation. So if we have students coming from other universities, CampusWire might restrict you. So I don't know if I have a good good solution here for that. Okay, all right, I'll have to think of something, but I guess if you don't have a UCLA email, you'll have to just email me and the TAs directly, and I apologize for that. Okay. All right, we've got the view quizzes. So your first view quiz was due yesterday at 11:59, and then today's view quiz will be due on Friday at 11:59. And you know, the view quizzes are worth a lot. They're going to be worth 18% total. One of them's dropped, so that ends up being, you know, each one's being worth 2%. So please don't forget to do your view quizzes. And that's because I value you guys coming to lecture and viewing the lecture. Even if it's not live, I put emphasis on. I feel like I hope the lectures are worth your time. Okay, so anyway, make sure you do that. Okay, yeah, and don't do this to yourself. Don't marathon lectures. I remember seeing on the UCLA Reddit subreddit that somebody posted this. They wrote, "I have a final at 11, and I haven't watched lectures since the midterm." That's just don't do that to yourself. It's a miserable experience. Okay, there is a practice Gradescope quiz, and a bunch of you have taken it. I would say about 40 or so of you, but that also leaves about 70 to 80 of you who have not taken it. And you don't need any stats knowledge to to answer the Gradescope quiz. You know, if you take it, you'll get 100%. But basically, the idea is it just makes you. The intention is to get you familiar with the Gradescope format, in that you click the link, you'll download the PDF file, and then once you've downloaded the file, you'll either answer the questions, you'll either print it out, answer it directly on a printed out paper, or you'll take a blank sheet of paper to answer your questions, or you'll have a tablet and you write directly on it. I don't know if there's another way that I'm not thinking of, but these are the ways that I'm thinking of as far as how to answer it. And then you need to get your answers back online. And so for that you'll need, I'm assuming most of you don't have a scanner. If you have a scanner, then great. But I'm assuming most of you will have to use your phone as a scanner, which is totally fine. You just have to be able to convert your pictures into a PDF. And to do that, on iPhones, the Notes app has a way to convert to PDFs. And on Android, you can use like Google Docs. Google Docs will be able to convert to PDF, or you can download a third-party app like there's like Cam Scanner and Office Lens. There's a whole bunch of things out there that are able to turn your phone into a scanner, but using and exporting them as PDFs. And for a lot of students, the hardest part is then getting the PDF from your phone onto the computer. And generally, if you have a cloud connection, you can log into wherever your cloud documents are stored, and that will work. And then you can do it. So I want you guys to get familiar. So when you do quiz 0, which is not worth anything or have no negative effects on your grade, if you do it correctly, you'll get 1 extra credit point at the end of the course. But there's no negative effects if you do it wrong. But please pay attention to that process so that you know what to do when the actual quiz on Friday, or I guess between now and Friday, takes place, that you'll know what you actually need to do. Do you need to worry about naming the file? No, you don't need to worry about naming the file. You just need to make sure it uploads to that you are logged into Gradescope when you upload it, okay? Because Gradescope doesn't actually show us the files directly, like it doesn't give us like the file name. It just shows us the PDF and allows us to grade it. It is important when you upload to Gradescope, it's gonna ask like, what page is this answer on and what page is this answer on. So for this first quiz, I want you to use 2 sheets of paper, or at least 2 sides of paper, even though they're like 3 questions and you can answer them easily on 1 page. I want you to intentionally use 2 pieces of paper to do that, because that's going to be most of the other quizzes. And then suggestion that Adobe Acrobat is really helpful. It's free and you can write directly on the PDF. Yes, if you've got a tablet or a computer where you can write on the screen and stuff, Adobe Acrobat certainly allows you to do something like that. But I recognize not everybody has a device where you can write directly on the screen. So that's an option. That's an option. Okay. And so the first quiz, I think will be available later today, and it's just due basically Friday before midnight. Okay. And for some of you, this represents the first kind of math-based class that you've had in a long time. For some of you, you have not taken any math since high school. And so maybe you have forgotten some of the basics, okay? And so, as far as doing well in this class, the amount of math required, it's not a whole lot, okay? You got to feel okay with fractions and decimals. We use fractions, decimals, and percentages interchangeably in the class. And then you got to be able to solve equations, and inequalities and linear equations and graphs. And Khan Academy is a good resource for learning that stuff. Obviously, if you feel very comfortable with this, you don't have to worry about it. But if you feel like, oh yeah, it's been X amount of years since my last math class, it could be worth taking a few minutes to go over this stuff. Okay. All right, let's go ahead and get started with today's lecture content, okay? And the goal that we have in mind for today is being able to describe a distribution of values, okay? And so the kind of the central idea in today's lecture is this idea of a distribution, all right? And so on Monday, we talked about gathering data, either from an observational study or controlled experiment. And then, the data that we have is a sample that's hopefully representative of the population, right? And so the data that you have, you can think of it as a collection of values, okay? If you're looking, especially if you're looking at one variable. So if you look at one column in your data, let's say everybody's heights, or you're looking at the variable, you know, everybody's income or something, okay? It's going to be a collection of values, right? And the way these kind of values are organized is with a distribution, okay? And a distribution is going to tell us what values appear frequently and what values appear infrequently, okay? So a distribution can be represented with a table or a graphic. And, you know, instead of trying to mention every individual observation in the data, we can describe the distribution of values as one entity. So, you know, in our class, we have, you know, 100-something students enrolled. And, you know, we could pretend that we asked every student, you know, fill out this survey where you say, you know, my name is this, and my age is this, and I am this tall, et cetera, et cetera, et cetera, okay? And so we could take one of those columns, like your age, and make a distribution out of it. And the distribution will tell us, you know, what values appear frequently and infrequently. So it'll probably say, like, there are a lot of people who are 20 years old and a lot of people who are 21 years old. And there might be, you know, there will be quite a few who are 19 and 18. There might be a couple of people who are 17. There might be a few people who are, you know, significantly, you know, probably 18 to 25 will be, there will be a lot of people. And then there might be a handful of people who are older than 25, you know, as far as the students go. But it, you know, we'll have either a table or a graphic that kind of represents this, okay? And so, so we're going to cover 2 chapters today. Chapter 2 covers visual diagrams for describing distributions, and chapter 3 covers describing distributions with numeric summaries. And it feels like it's going to be a lot, but I think these 2 chapters are fairly quick and easy, so we can squeeze in 2 chapters today. All right, so the big ideas that we're going to look at in chapter 2 is we are going to look at histograms for numeric data. And I guess going along with histograms are dot plots, okay? And I don't have specifically any dot plots in today's lecture, but they definitely appear in your textbook and in your homework. And they're very, very similar to histograms in nature. So please make sure you are familiar with dot plots. Maybe I'll add this. So histograms and dot plots for numeric data, and then bar charts for categorical data. Okay, so will I post the R code to CCL8? This is not this is Markdown, and I will not post my raw file onto Markdown. You'll get the PDF, the published PDF. Okay, so just an example here. Okay, an example that we've got going on is this is from the textbook. There is, I guess we looked at how many goals somebody scored. First year NCAA female soccer players in Division III. So you know, UCLA is Division I. Every sport UCLA does is Division I. I'm pretty sure. Yeah, so UCLA is Division I, but Division III is for, like, you know, schools where athletics are not a major focus. Okay, so if you've heard of the football team, it's going to be Division I, and if you haven't heard of this school at all, but they do have an athletics program, it'll likely be either Division II or Division III. So so anyway, we're looking at some Division III students, and this is how many goals they scored. And what we want to do is we want to be able to interact with these numbers. So we're going to just punch these into R, okay? And and it doesn't, the line was so long it didn't fit on one line here. But basically, I think in this week you learned how to create a vector, right? Using C. So you do C parentheses and then you just type in your numbers, okay? So we typed in all of the numbers and then we're going to store it using the arrow. It's the less than dash that kind of acts as an arrow, and we're going to store it into an object that we give the name goals, okay? Goals as in how many goals they scored. All right, and there are some ways to create summary tables and frequency distributions. So, so the first is we can create a frequency distribution using this function tally, okay? And tally is a function that is included in this library called Mosaic, all right? So let me explain a little bit about R and libraries and all of this stuff, okay? So, so R and RStudio come with a basic set of tools and commands. So creating a vector, creating kind of grouping numbers together into a single thing, that's a basic skill, okay? And then there are, there's a whole bunch of other functions that R is able to do in what we call base R, right? But then there's also kind of additional commands we can learn. And those are stored in libraries, okay? And so you can think of this almost like a book of spells, okay? Like if you were a student at Hogwarts or something and you go to the library, Hermione goes to the library and checks out, you know, reads books and stuff. It's almost like you're checking out a book, okay? And we're gonna call this Mosaic. And this library or this book called Mosaic contains additional commands, almost like a set of spells. And so tally is something that's included in here. And so in order to have R be able to use that function tally, we have to say, hey, look in this specific package, okay, that's part of our library. So first you have to kind of install that package into your library, which says, you know, we need to basically get this package or this book into our library, which is installed.packages. That should have been covered by your TA. And then once it's in there, you can say, all right, now look in this particular thing, and inside there you'll find this function, okay? And so, so we can run this. So if it says there's no package called Mosaic, then that means you don't have this package in your library. You have to install this package. So you have to, so the command is going to be install.packages, and then you type in Mosaic, okay, in quotes. Install.packages, quote, Mosaic. All right, I already have it installed, but I can hit enter again, and it will install it again, and it will say a whole bunch of stuff. Our tools is, you know, so red text. Not all red text is bad. This is one thing you've got to learn, okay? Red text is just the computer informing you stuff, all right? Sometimes it means there was an error. Sometimes it means something unexpected happened. And sometimes it's just friendly messages that say, hey, I'm doing what you asked me to do, okay? And, but the computer, for whatever reason, the computer decides, like this stuff, it looks scary because it's in red text. But this is, there's no error has happened, okay? No error has happened. So not all red text is bad. It's fine, okay? All right, so so anyway, we load up Mosaic, and then you can call tally on that vector, and it produces this. And this is a frequency table. It says the number 9 appears once, the number 11 appears 4 times, the number 12 appears once, and the number 13 appears 5 times. Okay, and if I scrolled back, we can indeed see that. There's 9 one time, 11 4 times, 12 once, 13 5 times. Okay. I'm not expecting you guys to follow along on RRR Studio right now, okay? I would rather you guys just sit and watch. But yeah, if you want to try these things out on your own time and things like that, you can try it out, okay? All right, so here I've created this, and then we can visualize it using the function histogram, okay? So here I've got histogram, and there's a few different options in histogram. One of them is width. This is how many numbers, the bin width per se, okay? And so this is going to basically say each bar that's drawn on the histogram should have a width of 1, meaning it's going to include only one number here. And so here we can see the result of the tally and the result of histogram line up, okay? So we have, it's cut off a little bit, but there's a bar at 9 that has a height of 1. There's a bar at 11 that has a height of 4, a bar at 12 with a height of 1, a bar at 13 with a height of 5, okay? So all we're doing is we're just turning the results of this, this frequency table, the frequency distribution, into a histogram, which is a visual presentation of this exact same information. So it's important to note that the information here is the exact same information that appears in this diagram, okay? And it should work, okay? All right, okay. I appreciate you guys helping each other out in the chat, and that's great. Don't feel like, again, don't feel like you have to follow along, but yeah. So that's what we've got going on. Okay, so we've got the information presented here is the same as the information presented here. This is just a visual way of presenting this. Okay, there's nothing here that's not present here. Okay, however, our brains are able to detect visual patterns often a little bit easier than they are able to process numeric information, okay? Because, so one thing you'll note, when you look at the picture, you recognize, oh, there's actually quite a big gap between 21 and 35, okay? That information is present in our frequency distribution here, okay? We've got 21 and 35, and our brain can say, oh yeah, 35 versus 21, 35 is 14 points bigger than 21, and our brain could recognize this, okay? However, that requires additional like mental processing before we can before we see it. And so sometimes the visual representation allows us to quickly identify certain certain things, and we'd say, oh, wow, that 35 really does stand out versus everybody else when we present it visually, okay? Because, well, it's actually interesting if you think about it, the way we process information. Just the fact that we can read numbers is amazing, right? Like your brain, your eyes are looking at this squiggle, this squiggle, that, and you know, and your eyes look at that and go, oh, now we have this mental concept of this numeric quantity 35, and you've processed that, right? It comes in and your brain says, oh, this is the number 35, and you can, well, anyway, I don't know. I'm impressed by the way our brain works. So, but it's also asking a lot for your brain to keep track of every single one of these numbers, and for this to happen, you know, in order asking your brain to keep track of kind of the difference between all of these things is a little bit tough. But the visual representation, you know, puts in the kind of physical distances here, right? Okay, I'm not going to answer any questions about kind of troubleshooting the code right now. That's not the point of the lecture. If you want to stick around after lecture is over, I can take a few minutes to answer some of your code questions, and also on Friday's office hours, I'll be around to answer your questions. So I don't want to get too sidetracked and trying to troubleshoot everybody's computer issues here. Okay, with the histogram, you can modify some of the settings. So one thing I can do is I can change the width of the bar to 3. Okay, so here I have the width being 1, so each bar represents basically one number, or has a width of 1. So so technically this would represent kind of values anything, I think, between 8.5 and 9.5. And here the first one, the first bar is centered at 9, and it has a width of 3. Okay, and so if I have a bar with a width of 3 centered at 9, okay, half of 3 is 1.5, and so it's this first bar will contain all values that are between 7.5 and 10.5, because I've got a bar centered at 9, and I want to have the total width to be 3. So it's going to go from 7.5 on the low end and 10.5 on the upper end, and there's only one number between 7.5 and 10.5, and there's one value at 9. Okay, but then the next bar goes from 10.5 to 13.5. From 10.5 to 13.5, there's 10 values. Okay, there is from 10.5, there's 4 11s, 1 12, and 5 13s. Okay, and those are all values between 10.5 and 13.5. And there's 10 of those values, and so we have a bar with a height of 10. Okay, is there a way to change the values from 8 exclusive to 9 inclusive, or will R automatically set it for you? So there's different options in histogram that you can do, right? So if you want to go from 8 to 9, exclusive to inclusive, you can say there's a width of 1, you want it centered at 8.5, and then there's an option to say either I want to include the value on the left or on the right, right? So so I think by default it's going to exclude the left end and include the right end. So if you want to go from 8 to 9, you can say I want it. There's an option to center it. Okay, you can say I want the center of the bar to be at, say, 8.5 or something. Okay, so by default, R chooses it for you if you don't give it anything. So here, this first bar is centered at 9, which means it goes from 7.5 to 10.5, and the next bar goes from 10.5 to 13.5. And this one goes from 13.5 to 16.5, and so on and so forth, because they have a width of 3. But you can change it, again, one of the options is you can say center equals 10, and that will say I want my first bar centered at 10, and it has a width of 3. So to have a width of 3, it goes 1.5 below and 1.5 above. So we're going to go from 8.5 to 11.5. So that's centered at 10. 1.5 below is 8.5. 1.5 above 10 is 11.5. And so here, when I say have a width of 3 and center equal to 10, you know, there's 5 numbers here. There's the 1 9 and the 4 11s, okay? And those are the values that are between 8.5 and 11.5, okay? So there are ways to do it. And it's interesting that this plot, the plot on this page and the plot on this page, represent the same underlying data, but they look a little bit different, and that's just because we've centered the first bar at slightly different locations. So that's something to just keep in mind, that where you choose to center your bars can have an effect on the visual presentation. Right? Just like taking a picture, right? 2 people can be looking at the same subject, but just the way somebody frames the image, frames the subject, has an effect on the visual presentation. And the same is true for histograms and plots, is that, and we're not trying to be deceptive, it's just slightly different choices can make different presentations, okay? And so these are just things to keep in mind, all right? All of these histograms represent the same underlying data, but it's just being presented a little bit differently, right? One is like your you know, how much focus do you put on one part or another? So, okay. There's a few choices here. So far, everything here has been shown as a count, okay? And another thing you can do is you can choose to have a relative frequency histogram, okay? A relative frequency histogram, rather than showing the count, shows a percentage, okay? And so here we have a total of 28 observations, and this first bar has 5 observations, right? It's got 1, 9, and 4 11s, so a total of 5 observations. And if we do 5 divided by 28, what's the percentage or what's the proportion represented? 5 divided by 28 is 17.8%. And so rather than having a height of 5, it has a height of 17.8%. So if we look at this, this plot and this plot are the same, except what has changed is on the left, here it says count. This count has a height of 5, and this first bar has the percent of total has a height of 17.8%. Okay, and that's the change there. That's the relative frequency histogram. Okay, and then there's another thing called the density histogram. Okay, so if you do the relative frequency histogram and you add up all of the heights will add up to 100%. Right, so this thing takes 17.8%, and I don't know what numbers these are, but you add them all up, they add up to 100%. Okay, here is another option to present. Okay, and this thing is called the density. Right, and the density, what's a density? The density is basically the same thing as a relative frequency histogram, except rather than having a height of 17.8, we're going to divide the height by the width of the bar, right? So here right now, our bar has a width of 3. It's got a width of 3. And so I'm going to take that number, right? So this first bar has a height of 17.8%. I'm going to take that number, 17.8%, and I'm going to divide by 3. So 17.8, that's basically 18%. 18 divided by 3 is 6. And so my first bar has a height of basically 6%, or 0.06. So just by convention, densities are presented as decimals and percentages get presented as percentages. But we're dividing by the width of the bar. So it's the same, basically the same shape, but that first number, 17.8, we divide by 3 and we get something around just under 6%. And so this first bar has a height of 6%. Okay, so why are we doing something like that, right? So why would we take the percentage? Because it makes sense that if you take all the percentages and you add them up, you get the total percentage adds up to 100%. Okay, the effect of dividing by the width is that the total area will add up to 1. Okay, so if you take the area of this bar, the area of this bar is going to be 17.8%. Okay, because it has a height of basically 6% and it has a width of 3. Okay, and so the area represented, okay, the area here is going to be equal to the same as the heights here, right? So this height is 17.8%. This height is 30-something%. Here, if you look at the area, it's the height of around 6% with a width of 3. So the area of this rectangle is going to be 17.8%. And the area of this rectangle is going to be, 30-something%. And when you add up all of the areas of the rectangle, all of the areas of the rectangle add up to 1, okay? And sometimes that's a desired property. So all of these things are kind of just like they should add up to the total. If you do the counts, the counts add up to the total number of observations. If you do a relative frequency, the heights add up to 100%. And if you do a density histogram, the areas of the rectangles, the areas of the rectangle will add up to 100% or add up to 1, okay? And that's kind of the difference between these things. And so they all present the same information. Like if you don't pay attention to what's happening on this axis here, and you just look at the shape of all of these things is the same, okay? It's just what's happening with what's represented vertically here. Here it says it's the count, here it says the percentage, and here it says the density. And they're just different values so that, you know, when we present them, they add up to one in some kind of way, right? Add up to the total. So that's what we've got going on, okay? I think in your lab, okay, when you do histograms, you'll often see a tilde character, okay? And what's going on here is that in my slides, the goals was a vector object, and you can have the function histogram work with a vector directly, okay? In your lab, you're importing something like this CSV file, the births.csv file, which in R is basically stored as a table. It's called a data frame, and each column is a separate vector. And in order to access, say, the weight column, one way you can do it is you can say, look at the NC Births table and use the $ to say, I want one of the columns. And here, let's say I want the weight column. So you can do NC Births $weight, and you can actually have a histogram work with that, NC Births $weight, and it would work with that, okay? Another way is you can use the tilde, and you can say, have a histogram work with the tilde weight, use the weight column, and look at the table data equals NC births, okay? And I think this is what is asked of you in the lab, and these two things would basically do the same thing, okay? An advantage of using the tilde is you can make kind of more complicated histograms, which I think is also asked of you in the lab, with such as a vertical bar, which is going to kind of separate out the histograms based on the variable habit, which is whether the mother chose to smoke or not during the pregnancy. Okay. There's also a function called hist, and this is in base R, so you don't actually need to load a library for hist, and you can call hist, and so and it will produce things. Controlling how many bins and breaks are formed requires a little bit of effort, but it's also possible inside there. Okay. Question: if weight is a vector, then why do we need to use the tilde? So the weight is a vector, is a column that is inside a data frame. Okay, so weight in of itself is not a vector, it's a column inside the data frame. And when you use something like this, it will pull out, it will extract the column from the data frame and make it a vector. Okay, we're getting a little bit into the weeds here and the nitty gritty here, but you know, the way R chooses to see things is it looks as NC Births as the data frame, it's a table. And if you want to pull out individual columns, you can use the $, or you can use the tilde notation and reference the original data frame. But weight in of itself, if you reference weight all by itself, R is going to say, I don't know what you're talking about, because it's very pedantic and needs to see like the vector itself. But weight in of itself is not a vector, it is one column, okay, a column inside the data frame, right? So when you load up the births data, the births CSV file, and stored inside NC births, it's going to give you something like this. It'll say NC births is a data frame, and these are the different columns available inside there, okay? And so so weight is one of the columns, okay, along with other values, okay, and this it's just one of the columns. That's all it's saying. All right, so here is, if we can look at M education. All right, so this is mother's education level, okay, measured in years of formal school. All right, and what we see is we see a tall bar at around 12 and a tall bar around 16, okay? And so 12 would be if you graduated high school, if the mother graduated high school, then they have 12 years of formal education. And if they completed their bachelor's degree, then they would have 16 years of formal education. And in this data set, we did not have any mothers who had completed more than a bachelor's degree in this particular data set. And you have a lot of other values as well. Okay. So this is what the histogram would look like. And there's something called the density curve, which is kind of a smooth line representation of the distribution. So here is kind of, if we have this and we say, I want this kind of represented with kind of a smoothed out line, it might look something like this. Okay, we see the spike at 12 and the spike at 16, and it kind of smooths things out, right? And when we talk about, so this is just another way of representing the underlying data without, I guess, getting bogged down with individual values here. So this is what we call a density curve. Okay, here's another histogram. This is a histogram of baby weights that were not born premature. Okay, so these are full-term babies. Okay, and we can specify that we want only the full-term babies by using the subset function. So here, for the data, I'm saying rather than looking at all of the births inside our data set, I want to subset it so that the variable preme being, was this baby born premature, that is no. Okay, so we want only the births where the, you know, that were not premature births, okay? And we're going to subset that, and we're going to look at the distribution of weight. And what we see is a histogram that looks like this, where most babies are around, you know, 115, 120 ounces, okay? So that's about 7.5 pounds or something, okay? Or what is it, 7 pounds? Let's see, 115 divided by 16. Yeah, okay, just over around 7 pounds, okay? So this is something around there, okay? And of course, there's babies that are heavier and babies that are way less, and some are much heavier and some are much less. But, you know, by and large, most of the babies born full term are somewhere around 7 pounds, a little heavier, or a little bit lighter, okay? And this would be the density curve representing that, okay? So I'm going to use these as kind of examples to the way we would describe the shape of our vectors, okay? So if there's only one peak, we would say the distribution is unimodal. And if there are two peaks, the distribution is said to be bimodal, okay? So, and if there's more than two peaks, we would say it's multimodal. So when we look at the density curve for mother's education, this would be bimodal because there's two peaks. We've got a peak around 12 years and a peak around 16. So this would be said to be bimodal. The distribution of full-term babies, that's one peak, has one peak, so we would say this is unimodal. Okay. Another aspect that we could bring up when we're describing shape is if the distribution is skewed or if it's symmetric, okay? If the left and the right-hand side look similar, it's going to be skewed. I mean, it's going to be symmetric, right? And if there's a long, what we call a tail, the distribution is skewed. So here's the density curve of the mother's education. And we would say this skinny part that kind of goes off, this is what we call the tail. The tail is on the left-hand side, so we call this skewed left, okay? So most of the mothers in the data set have around 12 to 16 years of formal education, but there were some mothers with very few years of formal education, okay? And that appears on the left-hand side, that's on the lower side. So this is skewed left, okay? Whereas the distribution of baby weights, okay, is fairly symmetric, okay? The left side and the right side look very similar, and so we would say this is symmetric. This is, in a real life data set, this is about as symmetric as it gets, okay? It's very difficult to find something that's truly 100% symmetric, okay? So I know if you held up a mirror, it's not going to be exactly the same, but in a real life data set, this is about as symmetric as it's going to get. So this would be a symmetric data set here, okay, as far as describing that. Okay, if there are observations that are unusual compared to everyone else, we might consider them to be outliers. So anything that stands out very far out to the left or the right might be considered to be outliers. Okay, so those were histograms, and that's all used for numeric data, okay? Let me talk about bar charts. Bar charts, on the other hand, are for categorical data. And I should say, in your reading, if rather than using bars for the histogram, if you choose to represent each value with dots, then you get a dot plot, okay? And you'll read about them in your homework, okay? Okay, bar charts are for categorical data, all right? It does not make sense to talk about shape like symmetric, skewed, unimodal, bimodal, and things like that for bar charts, okay? Because with a bar chart, the order of the bars can be rearranged. So our defaults to using alphabetical order, but other orders are just as fine. So in our data set, you know, when we looked at the genders of the babies that were born, okay, we had female and male babies, you know, represented in this data set, right? This is from 2004, and in our data set, only male and female babies are represented, and so this is what the bar chart looks like. We have female babies on the left and male babies on the right, okay? But if somebody wanted to present the bars in a different order, that would be completely valid. There's nothing that dictates that we have to present it in alphabetical order or in any other kind of order. It can be presented in different ways. Okay, here we have whether the mother chose to smoke or not during the pregnancy. Okay, and so we have non-smoker versus smoker, and this is what's represented, you know, with our bar chart here. Okay, and again, the order of these bars does not matter, right? And so so one question that we have is, if you look at this bar chart and you look at this bar chart, okay, which bar chart shows more variation? The one on gender, does this show more variation? Or does the one on smoking habit show more variation? Okay, all right. And so the answer, okay, again, we want to think about the variable itself, okay? The variable itself, the answer is that gender, the variable gender shows more variation, okay? And as far as the gender split goes, okay, these two bars are almost the same height, okay? And as far as a categorical variable goes, maximum variation happens when all the categories are equally represented, okay? And so when you, like if you imagine stepping into a room of all of these babies and we say, all right, who has a male baby? Raise your hand, and people would raise their hand. And who has a female baby? And some people would raise their hand. And then we say, who, you know, not to shame anybody, but we would say like, okay, who smoked during their pregnancy? Raise your hand. And who didn't smoke during, you know? And when you ask who chose to, who didn't smoke during their pregnancy, you know, not almost everybody, but the vast majority will say I did not smoke, right? And so there's not a whole lot of variation in terms of who chose to smoke versus not smoke, right? So there's a lot less variation because one of the bars is, one category is far dominant over the other category, okay? Sometimes we think of variation as far as like, are the things different sizes, but that's not what we're going for. We're not asking, are the bars different sizes? We're asking, um, which categories are kind of, where is there variation in the categories that are represented, okay? And so the genders are, have more variation in that. There's closer to equal representation, whereas as far as, you know, who chose to smoke versus not smoke, there's a lot less variation in that. Most of the mothers chose not to smoke during their pregnancy. Okay. All right. Why don't we take a short break here? Can I say like 4 minutes? Well, I'm going to get started back up at 11:05, and then we'll take a look at chapter 3. So we'll take a short break here, and then I'll come back at around 11:05 for the second half of the lecture. So let me pause. All right, we'll keep going here. Okay, chapter 3. Chapter 3 is going to be all about numeric summaries. Okay. Numeric summaries like mean and median will describe the center. We'll talk about describing spread, how spread out our values are, and that's used in range, IQR, variance, standard. We'll talk about all of these things, okay? And then there's z-scores and box plots. So the big idea here is that a numeric summary allows us to describe, I don't know, maybe not the entire distribution, but like the a distribution, at least the essence, the key ideas of a distribution with just a few numbers, okay? By definition, a numeric summary is reductive, okay? Numeric summary means that we're going to be leaving out details, right? And it's useful. Numeric summaries are useful because sometimes you just want to make a quick comparison between this sample of data and this sample of data. And you don't want to get bogged down by looking at all of the individual values in this sample and all of the individual values in this sample. You just want to say, you know, can I compare this group versus this group, okay? Very quickly. And a numeric summary is useful in that way, okay? And so we're going to look at ways to kind of summarize the aspect of where the center is using the mean and the median. And then we'll look at how to summarize the aspects of spread using the range, IQR, standard deviation, left out variance in this list. That's what we're going to look at. Okay, there's also different aspects that can be summarized, but as far as an intro class goes, I would say center and spread are the most important ideas. And you know, if you choose to major in statistics, if you choose to pursue kind of data as that, you'll learn how to summarize other aspects of the data. But at the intro level, these are the key components, okay? So here are just some other ideas of numeric summaries that you guys are probably familiar with. Oh, I haven't given, thank you. All right, I am behind on giving you guys quiz answers. Okay, the first quiz question is B. B as in bear, Bruins, the UCLA Bruin Bear, B. B is the first question. So Q1 is B. Okay, whoops. I meant to send that to everybody. Q1 is B. Okay. That's the first quiz question. Sorry for that. Okay, and I'll make sure to give you the other two quiz questions as we go, right? Okay, so for example, your GPA is a numeric summary, okay? It reduces your entire academic career, including all of your triumphs and failures, into a single number. It is very reductive, right? And this is what kills me, is that, you know, I know some of you are thinking of going to grad school or things like that, and so you're very concerned about your GPA. I wish that wasn't the case, right? Because in real life, your GPA has very, very, very little bearing on who you are. It actually has no bearing on who you are as a person, right? Who you are as a person is so much more than your GPA, okay? But when it comes to grad school admissions, you know, medical school or law school admissions or things like that, okay? The reason why the GPA is there and is useful is that they have to make quick comparisons from one student to another student. And rather than having to take the time of getting to know somebody in their full detail, they just go, oh, let's look at these GPAs and just go quick, right? This person's GPA is, 3.7, and this person's GPA is 3.9, and this person's GPA is 2.8, and things like that. And it doesn't matter what, like, they're not bogging themselves down with the details. And but schools will rarely, I think they recognize that this is not a good way to go, right? And so they'll rarely make a decision based on GPA alone, because it is so reductive. Okay, and so using one number to represent a full human is never a good idea. But there are uses and applications, but I wish this wasn't so, because it reduces who you are, right? Into a single number. That's never a good way to go. Okay. So if you're looking for a romantic partner, nobody would use a factor in GPA in romantic. Well, they shouldn't use GPA as a factor in their romantic partner consideration, because and realize that these things are much less important, right? Okay. Other things, like if you like movies, you might be familiar with the Rotten Tomatoes score, and what that does is it takes like all of these movie critics will either say, I liked the movie, I didn't like the movie, and the Rotten Tomatoes score is basically a proportion of what proportion of critics liked the movie. Okay. And it can be useful. It can be useful to compare one movie to another. You can say, oh, this movie got a 87% on Rotten Tomatoes, and this one got a 93%, and this one got a 45% on Rotten Tomatoes. Okay. But it reduces the movie down to a single number, and it's not going to tell you whether or not you like the movie, right? So if you hate horror movies, okay, if you don't like scary movies, right? I go to a movie to have fun. I don't like the horror genre. So even if the movie has like a 90% on Rotten Tomatoes, but if it's a horror movie, I'm gonna be like, it's probably not going to be for me, because that's not my that's not what I like, right? So reducing things down to a single number may or may not be the best thing. Still can be useful, right? Still can be useful if you're kind of on the edge, if you saw the trailer and you go, oh, that seems interesting, but I'm not sure if I want to spend $20 to go watch this movie. Man, I miss going to the movies. But anyway, that's what we got. Okay. All right, so let's talk about summarizing the center, okay? The center of a distribution we can describe using either the mean or the median, okay? The mean, we can think of this as a balance point, okay? So if we take a histogram, all right, you take a histogram and you imagine putting the histogram on a seesaw, okay? The point where you would put that little, the triangle, the fulcrum, so that the histogram is balanced, that's gonna be the mean, okay? And on the other hand, the median is the middle point. Half of the values are going to be less than or equal to the median, and half the values are going to be greater than or equal to the median, okay? And in R, you can find the mean and the median very easily by typing in mean of the vector name or median of the vector name, right? If you're dealing with a data frame, you pull out the vector name using the $sign. I think you guys are familiar with finding the mean and the median already. Like the mean, you add up all the numbers and divide by how many you have. And the median, you put them in order and you kind of start at the end and you find the middle number, right? So here is the weight of full-term babies, okay? So here's our histogram. This is the mean, okay? So I put a vertical line at the mean. And this says if we were to put this on some kind of seesaw, right? And if this thing needed to stay balanced, where do I put the fulcrum? I would put the fulcrum right here. Imagine putting a little triangle and this thing would stay balanced right there, okay? The median, okay? is just ever so slightly shifted, okay? And the median here, this is if we counted all the babies and we said how many are less than or equal to, we would have half of the babies are less than or equal to 119 and half the babies are greater than or equal to 119. So this is the count here. So when it's a symmetric distribution, the mean and the median are very, very, very similar in value, okay? Mean and median in a perfectly symmetric distribution would be exactly the same value, but you know, it's ever so slightly off, so these values are slightly different, okay? Here is a skewed distribution. This one is skewed right, okay? It's very skewed to the right. And this is baseball salaries, okay? So in 2018, we looked at the salaries of baseball players, okay? And so this is Major League Baseball, and we're actually we are seeing baseball games being played, which is impressive. But these are Major League Baseball salaries, and you know, sometimes you hear about you know, superstars signing these big contracts, right? Like Mookie Betts just signed a big contract, you know, worth millions of dollars each year and things like that. Mike Trout, I think, is one of the highest paid athletes ever in that, you know, he has a very big contract. And so we hear about these things, you know, getting paid millions and millions of dollars each year, okay? But most of the players in Major League Baseball, you know, I don't think they're complaining, but most of the players are paid something around the league minimum, or not that much money, you know, something around like what is it, $500,000 or something like that, okay? So when you ask for what is the mean is $2 million, okay? And that gets put right here, okay? This is the mean. If we had to balance this histogram, because we've got, you can even barely see it, but there's a person out here, okay, making a lot of money, okay? In order to stay balanced, this is the fulcrum is going to be put right here. But if we asked, you know, the spot where half of the players, you know, okay, what's the median salary? The median salary is around $550,000, okay? 550,000 is, you know, 1/4, or, you know, a little bit more than a fourth, maybe a fifth. No, I'm sorry, a little bit more than a fourth of, you know, $2 million, but that's the median. So about half of the players make 550,000 or less, and half of the players make more than 550,000. But the mean and the median are quite different here because it is so skewed. And so what we see is that when the data is symmetric, the mean and the median are going to be like the same value. But when it's skewed, the mean gets kind of pulled in the direction of the skew. So if it's skewed right, the mean will be greater than the median. And if the data is skewed left or left skewed, the mean will be less than the median. And so what we have here is data that is skewed right. Here's the median, and the mean is pulled in to the right. It's pulled in the direction of the skew. Okay, so the baseball salaries are very right skewed. And general income is actually even more right skewed, okay? So with baseball salaries, there's kind of a lower limit of like 500,000. I don't know what the league minimum is, you know, somewhere around 500,000, okay? And then the max is, you know, this multi-million dollar contract, okay? But if you think of the general population of people, okay, there's the minimum is 0, okay? And minimum wage, if we're only looking at full-time employees, the minimum wage is, you know, something around, I don't know, 20,000 a year, okay? Probably even, you know, whatever. I don't remember. What is minimum wage in California? Is it $10? $10.50? So if you're working 40 hours a week in California at $10.50, you'd be making around 21,000 a year. And what's the maximum? There's no maximum, right? So in baseball, it might be like $30 million. In you know, if you're looking at a CEO of some company, right? Like Elon Musk, he gets paid in like Tesla stock and it's like billions of dollars. Okay. Um, it's even more skewed right. Okay. And so the difference between the mean and the median is even greater in that. Okay. All right. So anyway, I think you guys know how to calculate this, right? Mean, you add up the numbers, divide by how many you have. The symbol we use for the mean is X bar. Okay. And the median is you arrange them in order from left, least to greatest or greatest to least. You got to arrange them in order. That's important. Okay, and you find the middle number. And then there's, surprisingly, we don't have a symbol that everybody agrees on for the median. It's all this time, nobody has agreed on what the symbol for median should be. We just say it's the median. Okay. Let's talk about measures of spread, okay? So spread describes whether if the values are similar to each other or if they're very different from each other, okay? So just as kind of an exercise here, we're gonna imagine 3 different rooms, and I want you to think of the ages in each of those rooms. So the first one, imagine a 2nd grade classroom. You're looking at the students in the 2nd grade classroom. You know, what's the distribution of ages there, okay? In that 2nd grade classroom, nearly everybody in that classroom is gonna be 7 or 8 years old, okay? It would be surprising to find a 10-year-old in the 2nd grade classroom, okay? And so nearly everyone is around 7 or 8, okay? So classroom of stats 10 students, okay? I know we're not in the same physical room, okay? But just imagine that we are, okay? And I think on Monday I asked, you know, how many of you are 1st years and 2nd years and 3rd years? And, you know, a lot of you said you were 2nd years, and a good number of you said you were 3rd and 4th years and things of that nature. And if we imagine the ages of students in a Stats 10 classroom, there would be a wider range of ages. We'd say a lot of students will be between 18 and 22, but we'd also have quite a few students outside of that range, right? We have students who transferred in took a couple of years at or a few years at community college and transferred in, so they're coming in a little bit older. We also have students who either served in the military or did different kinds of things, worked at a job and then chose to come back to school, not straight, or chose to go to college not straight out of high school, but at a later point in their life, and so their ages are going to be outside of this 18 to 22 range. Okay, and so so if we think about the spread there's a little bit more spread. Okay, and then if you imagine going to the DMV, and I can't imagine going to the DMV now, but if you could imagine going to the DMV, what does that waiting room look like? And there's all kinds of ages. You have teens trying to get their driver's licenses. You got adults, renewing registrations and things, senior citizens, and then you also have, young children of the parents that are waiting and things like that. There's going to be a huge, huge range of things, okay? And so what we might say is there is very little spread in the ages of the classroom, and there's lots of spread in the ages at the DMV. And then there's, a medium or a moderate amount of spread in the ages of Stats 10 students, okay? And that's fine, okay? That's fine. We can talk about little spread and lots of spread and things like that, okay? But rather than using vague terms like little spread and lots of spread, okay, we can use a numeric quantity, and a numeric quantity will give us an exact number that we can use to kind of compare. So we can say in the classroom, there's a standard deviation of 0.3 years, okay? At the DMV, the standard deviation is 15.2. And for Stats 10, the standard deviation is 3.1, okay? So rather than just saying little and medium and lots, we can actually give it a number. And that's what these numbers are trying to quantify. They're trying to quantify the spread, okay? So you can think, an important one is the variance and the standard deviation. Okay, wait, before I get into that, let me give you the second quiz answer. Second quiz answer today is D. D as in dog. D as in dog is the second quiz answer. Okay, did you guys get that? Question 2, second quiz answer is D. D as in dog. Okay. All right, so let's talk about the variance and the standard deviation. Variance is the average squared distance from the mean, and the symbol for that is s squared. And then the standard deviation is the square root of the variance, and the symbol for that is s. So I guess really we just have a symbol for the standard deviation, and the variance is standard deviation squared, okay? But as far as definitions go, we can think of variance as the quote-unquote average squared distance from the mean. So let me, let's break this down, okay? Oh, here are the formulas. We can take the distance from the mean, we square it, okay, x minus x bar squared summed up divided by n minus 1, and the standard deviation is the square root of that, okay? Or x bar represents the mean of the values. Okay, so forgive this wall of text here, but let's say we have these numbers 1, 2, 3, and 10, okay? The mean of these four numbers is 4, okay? If I do 1 plus 2 plus 3 plus 10, that adds up to 16. 16 divided by 4 is 4, okay? So the mean is 4, and what we're going to do is we're going to find the squared distance from 4, okay? And so we're going to look at each of these numbers. So the number 1, how far is that away from 4? 1 is 3 units away from 4. And if we take that number 3 and we square it, the squared distance is 9. We look at 2. 2 is 2 away from 4. The mean, again, the mean in all of these things is 4. So 2 is 2 units away from 4. And if we square that, the squared distance is 4. 3 is 1 unit away from 4. And if we square 1, 1 squared is 1. And if we look at 10, 10 is 6 units away from 4. So we take 6 squared, and we get 36, okay? So the squared distances are 9, 4, 1, and 36. So we're taking the distance from the mean, and we're squaring the distances from the mean, and we get 9, 4, 1, and 36, all right? And then what we're asking here is, what is the average? What is the average squared distance from the mean, okay? So traditionally, for average, we would add them up and divide by how many we have, okay? But here I put average in quotes because rather than dividing by how many we have, we're going to divide by n minus 1. So I'm going to do 9 plus 4 plus 1 plus 36. I add those things up, and these will add up to 50, okay? 9 plus 4 plus 1 plus 36 will add up to 50, but I'm going to divide by n minus 1, okay? N is how many numbers I have. I have 4 numbers. 4 minus 1 is 3. We're going to do 50 divided by 3, and we get 16.67, okay? Is that okay? Is this process in terms of, if I tell you the variance is the average square distance from the mean, and the resulting number is 16.67, I kind of just want to make sure you guys followed along. And if so, give me a green yes check. And if this was no good, or if you have questions, let me know. Put your question in the chat, okay? All right. And if you want to know why it's divided by n minus 1, you can look up something called Bessel's correction on Wikipedia or something. If you major in stats, you'll learn about it. But beyond the scope of an intro class, okay? It turns out it gives a more accurate estimate by using n minus 1. All right, so here, how do I interpret the variance in the context of a question? Okay, so again, all of these things are generally more useful when you're making a comparison, right? So if you're not familiar with something, if you're not familiar with a particular thing, right? So I can say, I don't know, like in the NFL, right? There's passer rating for like a quarterback's performance, and if you're not familiar with that, it's not very useful to just say, oh, so and so's passer rating performance was 103, okay? Because you'd be like, is that good or is that bad, right? So all of these things, including the variance, is just generally you need to be able to compare it with something else, right? And so if I just tell you the variance is 16.67, you'd get, oh, okay. And all by itself, in the context alone, it's not very useful. But if I give you two things and I say the variance of this group is 16 and the variance of this group is 45, then you can say, oh, this group has values that are more spread out than the other group, okay? But if you're just given one group or one data set and I give you the variance of that all by itself, it's not that useful because there's nothing to compare it against, right? You need to have at least some kind of baseline, right? So for example, let's say, like if you go to another country, okay, the grading system is not on a 4.0 scale, right? So in Germany, 4.0, like straight A's would not be a 4.0. You actually, I think, I could be totally making this up. If you're German, let me know that I'm doing this all wrong. But I think in Germany, the highest grade you can get is a 1, and the worst grade you can get is like a 5. I don't know. I'm kind of making this up. Okay, so the highest grade you can get a 1, and so anyway, you need to know the context of these things, and then you can talk about kind of these averages. So or these terms. So 16.67 all by itself, not going to be a whole lot of useful, okay? But when we're talking about, I've got one set and another set and we're comparing them, that's when it's useful. And the variance, again, is a way to measure how spread out the numbers are or how not spread out they are, okay? So this is the variance. Standard deviation is you just take the square root of that. So on the previous page, we find the variance and then standard deviation is the square root, okay? Here it is in R. My vector is 1, 2, 3, 10. I can say, what's the variance of the vector? And I get 16.667. What's the standard deviation? And that's going to be the square root of that. And I get 4.08. All right. Okay. So here's one where it's a little bit easier. So, I mean, you can try this out on your own. Okay. So here are, imagine two families. In both families, there are 5 children. And in both families, the mean age of the kids is 9, okay? And so we have the Baker family and we have the Cook family, okay? And so the Baker family, the children's ages are 1, 3, 9, 13, 19, okay? And if you add them up, indeed, the average age of these kids is 9, okay? 1, 3, 9, 13, 19, okay? And in the Cook family, 5 kids, the average age is 9, and the kids' ages are 7, 8, 9, 10, and 11, okay? And so we can imagine what life is like in the Baker family and what life is like in the Cook family. And even though they both have 5 children and the average age of the 8 kids is 9, life looks quite different for both the Baker and the Cook family, right? So in the Baker family, this kid's going off to college maybe, helping take care of the baby, things like that, right? The 13-year-old is probably helping take care of the baby as well. Okay, whereas, in the Cook family, there's no baby. The youngest is, all 5 kids are are attending the same elementary school or something like that, right? So it's, so we can look at this and we can compare these two, and we can clearly say that, life is going to be different. The Baker family kids' ages are more spread out than the Cook family, and mentioning only the number of children and the mean age does not give the full picture, right? And so we can include the standard deviation, and we can say the standard deviation of ages in the Baker family is 7.35, standard deviation of ages in the Cook family is 1.58, okay? And, you know, by definition, you can think of this being like the kind of the average distance from the mean or typical deviation. That's where the standard deviation, we're talking about deviation from the mean, okay? This is your kind of typical deviation from the mean. But again, it's more useful in terms of comparison. We can say these values, the standard deviation is higher than over here, and therefore they are more spread out. So that's what we have for standard deviation. Okay, range and IQR, this is another way. These are other ways to measure spread. So the range is the largest value minus the smallest value. So you do the max minus the min, and just the difference between the biggest and the smallest gives you a sense of the spread. The range is the largest minus the smallest. If there's any outliers, the range is going to be drastically affected, right? So you can have almost everybody be between, you know, two numbers, but then you might have one value that is like way high or one value that's way low or something. Okay, if you have any outliers, then the range is going to be drastically affected. All right. And on the flip side of the range, okay, or related to the range, is the interquartile range, the IQR, okay? The IQR is the difference between the third quartile and the first quartile, okay? Third quartile and first quartile. First quartile is the 25th percentile. That's the spot where 1/4 or 25% or 1/4, that's where the first quartile comes from. The 1/4 is less than or equal to the first quartile. And Q3 is the third quartile, and that's the 75th percentile, or 75% or 3/4 of the data are less than or equal to the third quartile. So Q3 to Q1, that's going to give you kind of the middle 50%, the middle half of values. And these are often reported in college admission statistics. They'll say the SAT scores of the middle 50%, the 25th to 75th percentile. I think recently it was released for UCLA. It was like the 25th to 75th percentiles of the, you know, your math SAT scores or something like 670 to 780 or something like that, you know, and that's, you know, Q3 to Q1, okay? All right, so let's say we have these 12 test scores and we want to find, you know, Q1 and Q3 and IQR and all of this, okay? So number one, we got to put them in order, okay? And I've already put them in order from least to greatest, okay? So I've got these 12 test scores in order from least to greatest. All right, so first we're going to find the median. We're going to take the 12 values and we're going to find the median, okay? So I've got 6 values less than or equal to the median, 6 values greater than or equal to the median, okay? So our two middle values are 82 and 85. The median is going to be halfway between 82 and 85. So we just take the mean of 82 and 85, and it's going to be 83.5. So the median is 83.5. That goes right here. The median goes there. And so I've got 6 values less than the median, and I've got 6 values greater than the median. Okay, so that's, so I put a little bar right there representing the median. And now for the Q1, I'm going to take these 6 values and I'm going to find the median of these 6 values, right? So the two center values here are 75 and 77. So we're going to take Q1 will be 76. It's halfway between these two values. So Q1 is 76. I do the same thing on the right-hand side. I've got these 6 values, and I'm going to say, okay, well, take half of 6, and that's 3. And the median of those 6 values will be here. And so Q3 will be halfway between 90 and 94, which will be 92, okay? So Q3 is 92. Q1 would go right here and be 76, okay? So 76 is the first quartile Q1. 92 is the third quartile Q3. And our IQR is going to be the difference between that, which is 92 minus 76. I have an IQR of 16. So Q3, 92, minus Q1, 76, 92 minus 76, I have an IQR of 16. And then the range is going to be the max, which is 100, minus the minimum, the smallest value, 65. The range is going to be 35. Okay. So again, these are just different ways to measure the spread. And so here the IQR is 16 and the range is 35. And again, in of itself, reports a little bit, but it's generally more useful in the context of comparing one group to another group. So if you find the IQR of another group or the range of another group, you can say, oh, these values are a lot more spread out than another. Right? Okay. Sometimes you might take a set of values and they might talk about the 5-number summary. Okay. And the 5-number summary is going to be the 5 values are the minimum, the first quartile Q1, the median, which is the spot where half, that's technically also called Q2, the max Q3, which is the 3rd quartile, and the maximum, which is technically the 4th quartile or Q4. Okay, the 5-number summary is basically the 0th percentile, 25th percentile, 50th percentile, 75th percentile, and 100th percentile, the maximum. Okay, and so this is what we have, right? So if we have these scores, we can get the 5-number summary from R just by using this function summary, okay? And it will give you the minimum, 1st quartile, the median, 3rd quartile, and max. And it also, for good measure, throws in the mean, okay? So the mean is technically not part of the 5-number summary, but the mean is commonly a value that people want to know. So, so when you ask for summary, it will give you the mean as well. So it gives you 6 numbers, the min, 1st quartile, median, mean, 3rd quartile, and max, okay? If you look at these numbers, the quartiles that R finds, 76.5 and 91 is technically different, right? When we did it, we got 92 and 76. And that's because there's actually a couple different methods for calculating quartiles. And again, we don't need to get into it. If you want R to find the quartiles the exact same way you did it, you can say, I want you to use this method, method 5, and it will get the values that match what we did, 76 and 92. Okay. In most cases, the difference between this and this will be pretty small, 76.5 versus 76. And especially if your data set is very big, these differences will be, quite small and doesn't really matter. But technical issues, slightly different, okay? Okay, how are we doing? Okay. There is the something known as a z-score, okay? A z-score is useful for determining whether an observation is unusual or not, okay? And it's a z-score is how far an observation is from the mean, and that distance is expressed in standard deviations, okay? So the formula, or the way we calculate the z-score, is you take your observation x and you subtract it from the mean, or you subtract the mean from it, okay? So the numerator, x minus x bar, is how far something is from the mean, okay? And so that's the distance from the mean. And we're going to divide by s, the size of the standard deviation, to see how many standard deviations that distance is, okay? And this is useful to compare observations from different sets of data. So here is here's an example, right? So in the Olympics, which have been delayed till next year, there is the decathlon event, okay? And so a question is, what's more impressive? A long jump of 7.4 meters or a high jump of 2.2 meters, okay? Now, I don't imagine many of you being kind of track and field enthusiasts and know all the details of what a good or bad long jump is, or what a good or bad high jump is, okay? So these just sound impressive to the average person, but compared to other Olympians, what is, what's impressive, right? So if you're not familiar with this, answering this question is impossible, right? So I could give you something, right? Like, the average long jump at the Olympics is 6.5 meters, okay? And the average high jump at the Olympics is 1.88 meters, okay? I've made these numbers up. Don't quote me on this. I have no idea what the average long jump or what the average high jump is. I think it's something around here, but it's not like I've got this long compendium of Olympic statistics here. Okay, and so this long jump of 7.4 meters is 0.9 meters higher than the average of 6.5, right? So if the average long jump is 6.5 and they've jumped 7.4, 0.9 meters higher than the average of 6.5, okay? And then here, 2.2 is 0.32 meters higher than the average of 1.88 meters, okay? So here we can say, well, this is the distance from the average, okay? Distance from mean, but we need even more information to be able to answer the question of which is more impressive, okay? So we need to know about the amount of spread that exists for each event, okay? So here again, I've made up these numbers, but we can say for the long jump, the average is 6.5 and the standard deviation is 0.4 meters. And for the high jump, the average is 1.88 and the standard deviation is 0.11 meters. Okay, again, I've made these things up. And so the long jump has a z-score of, okay, we take that difference, 7.4 minus 6.5, and we divide by 0.4. So this is a difference of 0.9 meters, but how many standard deviations is that? That's going to be 2.25 standard deviations higher than the mean. The high jump, 2.2 minus 1.88, is 0.32 meters above average, but the standard deviation is 0.11. So this is almost 3 standard deviations, 2.9 standard deviations away from the mean, okay? So the z-score for the high jump is 2.9. The z-score for the long jump is 2.25, okay? And so the z-score for the high jump is greater than the z-score for the long jump. So it is the more impressive feat, okay? So we can't just say, is it higher or lower than average? And we can't just look at the distance from the average all by itself. We need to kind of compare it to the context of its spread, okay? And so there's something known as the empirical rule, and that says if the data is unimodal and symmetric, okay, about 68% of observations are going to have z-scores between 1 and -1. Most of the observations, oh, okay, actually most will have z-scores between 1 and -1. So about 2/3, 68%, between 1 and -1. 95%, so that's 19 out of 20, will have z-scores between 2 and -2. And nearly all of them, not necessarily all, but nearly all will have 99.7 will have z-scores between 3 and -3, okay? And therefore, we're going to say z-scores greater than 2 or less than -2 are considered unusual, and z-scores greater than 3 or less than -3 are considered highly unusual. So these are some terms that might seem subjective, but when we're talking about unusual, we generally mean z-score is greater than 2 or -2. And if you have a z-score of 3 or -3, that's considered highly unusual, okay? So, both of these are unusual in that they're impressive. They have z-scores greater than 2, but this one's 2.25 and this one's 2.9. So this one is more impressive than this one, okay? And if it's greater than 3 or -3, it would be considered highly unusual. So that's what we have here, okay? The 5-number summary can get presented in something called a box plot, okay? So box plot is a graphic representation of the 5-number summary, okay? We draw a box with borders at Q1 and Q3, and a line is drawn with inside the box at the median, and we have what we call whiskers that extend from the box to the min and the max, unless there are outliers, okay? And outliers are, this is an arbitrary rule that's just kind of accepted by convention, is that if a point is more than 1.5 IQRs away from Q1 or Q3, they would be considered the outlier. So there's a left limit, which is 1.5 IQRs away from Q1. And then there's a right limit, which is 1.5 IQRs above Q3. And points that are above or below these limits are considered outliers. So let me give you a little picture here. So if you have this data, this is what your box plot might look like, okay? You have a line at Q1, 76. The box goes from Q1 to Q3, 76 to 92. And the median, you get a line drawn at the median, 83.5. And then whiskers go down to the smallest point, 65, and the largest point of 100. So this is labeled min, Q1, median, Q3, and max, okay? Here, if you look at the weight of the full-term babies, some of these baby weights are considered to be outliers, okay? And so this is technically the max and this is the min, okay? So this is the min and this is the max, okay? But you have the IQR, Q1, median, and Q3 is, forms the box, and the width of the box is the IQR. And if you go 1.5 times the IQR above the above Q3, that takes you to the right limit, and 1.5 times the IQR below the box takes you to the left limit, okay? And so this is what the box plot looks like for the full-term babies here, okay? And you know, there's more details on this as you do your reading, and so please you know, please do your homework and do your reading, and you can expect a few questions regarding box plots and whatnot on your quiz that that will be due on Friday. So so please, you know, I strongly recommend that you do your homework before you attempt the quiz. Okay, the link to the quiz is on CCLE under the quizzes and exams section. Okay, so under quizzes and exams, you'll make sure you come over here and you click the link to quiz 1. Okay. All right, and that's all I've got for you today. Oh, let me give you the last quiz question. Last quiz question today is A as an apple. A as an apple. So Q3, last answer there is A. So so that's all I've got for you guys today. Have a good weekend, everybody, and good luck on your quiz. And we will see you guys next Monday. All right. So that's all I've got. Thanks, guys.